Now let's talk about the reaction quotient QC. And we'll talk about QC. There's also QP, and for any K value, for any equilibrium constant, there is also a corresponding Q reaction quotient. So what is it? A QC is used to predict the direction of reaction, forward or reverse, as the reaction approaches equilibrium. And QC has the same expression as KC, except not at equilibrium. And so when given a set of initial conditions, plug into the QC expression to see how to get to equilibrium. So let me see here. So QC equals the exact same expression as KC, meaning its products raised to coefficients, still not putting in any solids or liquids, only aqueous and gas phase species, so all the same rules apply. Over reactants divided by coefficients. And what we usually use this for is at the beginning of a problem, we'll be given a set of conditions. And by conditions, what I mean is a set of concentrations for QC or a set of partial pressures for KC. Given a set of concentrations, and our interest is to find out how to get to equilibrium. Trying to find equilibrium concentrations. And I'll abbreviate concentrations there. And what we will see is that, let's start with QC less than KC. So we get some set of conditions, we plug them in, and QC is less than KC. That means that the denominator is too big. That's why QC is less than KC. So, concentration of reactants is higher or too high to be at equilibrium. Concentration of reactants too high to be at equilibrium. Colon, so the reaction must go in the forward direction. Reaction must go in the forward direction to get to equilibrium. Because all reactions are trying to get to equilibrium. Because equilibrium is the lowest energy position for the reaction. Now, we can also, and what we'll see is that when we say do the forward reaction, go in the forward direction, reaction must go in the forward direction, since the forward direction is often to the right, which is where products are, we will oftentimes call this shift right, or shift right to products. That's a common expression. Now, if QC is greater than KC, that means that the product concentrations are too high. Shift left, or do the reverse reaction. And sometimes we just say that, but the idea is that we're always doing the reaction to get to equilibrium. Because that is how reactions always go. They are always working to get to equilibrium. And if on the off chance, and this doesn't happen that often, QC equals KC, then our conclusion is that we have the perfect ratio of product and reactant concentrations, and we're at equilibrium. And again, this doesn't happen that often for these types of problems. Usually, we're trying to figure out which way we need to go to get to equilibrium. Here's an example. Typical. Kc is 14.5 at 210 degrees Celsius for the following reaction. Carbon monoxide. This is a very familiar one. So what direction should the reaction go to reach equilibrium if the initial concentrations are all 0.100 molar? So that's, again, we have initial concentrations, and we are not sure if we're at equilibrium or not. So QC allows us to determine that. And so we write out the exact same expression, products, concentrations, raised to exponents, divided by reactant. Concentrations raised to exponents. And we've been told they're all 0.1 molar. And now multiply this out, so we can see that 2 of them cancel. And I guess if we have 0.1 squared in the denominator, then QC is going to be 100. And just a word about units. So QCs and KCs, we never treat them as if they have units. And it's clear that QC in this expression does have units. And all I will say about that is that in a more advanced treatment of the material that we're doing, more advanced than is possible in this course, there's another factor for each of these terms that does cancel the units out. And I can talk about that more in office hours if you would like. But for now, we don't carry units for QCs, we don't carry units for KCs, and we won't. And believe me, if there were units to put, I would put them, because I heart units. Let's see. I heart units. There we go. Anyway, so here we are. QC is greater than KC because QC is 100, KC is 14.5. What that means is that we have too many products, or too high a concentration of products to be at equilibrium. So therefore, the reaction must shift left, left, even though on camera up here it's pointing to the right, but here it's left. Shift left, which means do the reverse reaction and convert products into reactants, which I know are 3 ways of saying exactly the same thing, but just in case any of these seems better to you, any of those is fine. Convert products into reactants. Good.